This is the fourth lecture on Bessel differential equation. Today we shall discuss the recurrence relation of Bessel differential equation, Bessel function for for general order. In the earlier class, we have used the generating function of Bessel function, which is applicable for Bessel function of integral orders only, and used to find out the recurrence relation for Bessel function of different orders. As for example, Jn plus 1 of x plus Jn minus 1 of x was 2n by x Jn of x, and Jn minus 1 of x minus Jn plus 1 of x is equal to 2 Jn prime of x. These were the relation that we have obtained earlier. Today we shall obtain the similar result for non-integral orders as well. That is, in this relation we have obtained for n is equal to 0, plus minus 2, etc. Now we shall obtain the similar result, which are is equal to 2 alpha by x, j alpha of x, and j of alpha minus 1 of x minus j of alpha plus 1 of x is equal to, where alpha may be anything. Alpha may be 0, plus minus 1, plus minus 2, as in the case of this it could be plus minus half, plus minus 3 by 2, etc. Or even maybe other fractions too. To start this relation, we shall to derive this relation, we shall start with the generating function for Bessel we shall start with the series expansion for Bessel function of a general order. Thus, the series expansion for Bessel function of a general order is j alpha of x is equal to summation over k is equal to 0 to infinity factorial k gamma k plus alpha plus 1 minus 1 to the power k x by 2 to the power 2k plus alpha. This is the series expansion for Bessel function of general order, and for alpha is equal to integer. Note that for alpha belongs to integer, gamma k plus alpha plus 1 becomes gamma of k plus n, n plus 1, and this is equal to k plus n factorial. And when alpha is not an integer, we cannot write this relation. This relation no longer holds. This is the difference between Bessel function of integral and non-integral orders. We multiply this relation, either side of this relation, with x to the power alpha, so that we have x to the power alpha, j alpha of x is equal to summation over k is equal to 0 to minus infinity. We write it 2 to the power 2k plus alpha k factorial gamma of k plus alpha plus 1 minus 1 to the power k and x to the power 2k plus alpha. When we differentiate this, the differential operator operates only on this part, so this is summation over k is equal to 0 to infinity. And we have ddx of x to the power 2k plus alpha. This part is actually equal to 2 times k plus alpha and x to the power 2k plus 2 alpha minus 1. So this 2 reduces this part by 1, so this is 2 to the power 2k plus alpha minus 1, then k factorial, and there is a term k plus alpha, so this is minus 1 to the power k plus alpha and x to the power 2k plus 2 alpha minus 1. Oh, I have missed this gamma factor, gamma k plus alpha plus 1. Now note that gamma of k plus alpha plus 1 is equal to k plus alpha gamma of k plus alpha. So there is an adjustment. So if we do this adjustment, we get and take 1 x to the power alpha outside. So we have 2 to the power 2k plus alpha minus 1 k factorial gamma of k plus alpha minus 1 to the power k, and here we have x to the power 2k plus alpha minus 1. We rewrite this as you see that the power of x and 2 are the same, and we write it k plus alpha prime plus 1 and x by 2 2k plus alpha prime, where alpha prime is equal to alpha minus 1. So that alpha prime plus 1 is alpha. So this part is j of alpha prime, that is j of alpha minus 1. So we have x to the power alpha j of alpha prime of x, this is x to the power alpha j of alpha minus 1 of x. So we obtained one relation. So we write this over here. So this relation now simplifies to x to the power alpha j of alpha minus 1 of x. Now we differentiate the left hand side of this relation with respect to x, so that we get first term is alpha x to the power alpha minus 1 j of alpha of x plus x to the power alpha j alpha prime of x is equal to x to the power alpha j of alpha minus 1 of x. Now if we divide all the sides by x to the power alpha, we get alpha by x j alpha of x plus j alpha prime of x is equal to j of alpha minus 1 of x. So we get this leads us to the relation that ddx of x to the power alpha j alpha of x is equal to x to the power alpha. This gives you alpha by x j of alpha x plus j alpha prime of x is equal to j of alpha minus 1 of x. Now we multiply this relation once again by x to the power minus alpha, move the sides and take the derivative of it. So when we multiply the sides by x to the power minus alpha, we have j alpha of x is equal to summation over k is equal to 0 to infinity minus 1 to the power k, and you 2 to the power 2k plus alpha k factorial k plus alpha plus 1 gamma of this and this x to the power 2k. We have multiplied both the sides by x to the power minus alpha, which makes this power of x from 2k plus alpha to 2k. And if we take the derivative of it, this part will be differentiated, so it results in a 2k and the power will be reduced by 1. Minus 1 to the power k. Here it will be 2k plus alpha minus 1 k factorial gamma of k plus alpha plus 1, and this is k times x to the power 2k minus 1. Now first adjustment, this makes this part and this part is adjusted to make it k minus 1 factorial. So this becomes now you see that k for k is equal to 0, this term is undefined because it becomes a factorial of a negative integer which is not defined. So the sum over here should start with 1, and we define a quantity k prime is equal to k plus 1, so that k prime ranges from 0 to infinity. We rewrite this as k prime is equal to 0 to infinity, so k is we introduced k minus 1 is equal to k prime, so k is k prime plus 1. It's okay. And this part is k and this is we define alpha prime to be k plus 1. Sorry, alpha prime is alpha plus 1. And we multiply this is by x to the power minus alpha, so that we have k prime is equal to 0 to infinity, and we do one minus sign is taken out, so this is minus 1 to the power k prime. This is alpha prime. One k prime factorial was missing, so this is k prime factorial gamma of k prime plus alpha prime plus 1, and this is x by 2 to the power alpha. Check out the adjustment, and this is j of alpha prime, so this is x to the power minus alpha j of alpha prime of x. This is equal to x of minus alpha j of alpha prime plus x. So we will end up with the result x to the power minus alpha j of alpha plus 1 of x. And also we get another result as ddx of x to the power minus alpha j alpha of x is equal to minus sign was missing, minus x to the power minus alpha j of alpha plus 1 of x. Now if we differentiate the left hand side, we get minus alpha x to the power minus alpha minus 1 j alpha of x plus x to the power minus alpha j alpha prime of x is equal to minus x to the power minus alpha j of alpha plus 1 of x. Dividing all through by x to the power minus alpha, we get minus alpha by x j alpha of x plus j alpha prime of x is equal to minus j of alpha plus 1 of x. So this gives you this is the result. Now if we add the two final results, that is, if we call this equation as 1 and this equation as 2, then adding 1 and 2 we get 1 plus 2 gives us, you see these two terms cancels out, this 2 added up, and this is j alpha. So the result is j of alpha minus 1 of x minus j of alpha 1 plus x is equal to twice j prime of alpha x. And if we subtract 2 from 1, then we get 1 minus 2 gives. You see that these two terms get cancelled, and we have these 2 plus, and the result is j of alpha minus 1 of x plus j of alpha plus 1 of x is equal to 2 alpha by x j of alpha x. Earlier we obtained this result for a Bessel function of integral order. So starting with the generating function, we first obtained this relation and then this relation. This relation was obtained by differentiating the generating function partially with respect to t, and this relation was obtained by differentiating the generating function partially with respect to x, and then we added this relation to get such relations. So the trip was starting from here, we landed up to there, and here we have obtained the relation in the reverse order. Firstly we get this relation, then from there this relation and a similar relation, and when they are added or subtracted from one another, we get these two results. These results are valid for all orders. As for example, okay, well, let me first keep this in. This is relation 3. This is relation 4. These are the important relations. We shall use relation 3 to find out a few Bessel functions of higher orders. Before going to this, let us recall that j of half of x is equal to 2 by pi x sine x, and j of minus half of x is equal to 2 by pi x cos of x. We obtained this relation earlier. First let me study the behavior of j of plus minus half at x is equal to 0. At x is equal to 0, we can rewrite it as 2x by pi sin x by x, as x tends to 0, this tends to 1 and this tends to 0. So at x tends to j half of 0 is 0, but here it has an essential singularity, and j of minus half, as x tends to 0, it tends to plus infinity. Now we use j is equal to alpha is equal to half in this relation. Equation 3 gives what alpha is equal to half. So this is j of minus half plus j of 3 by 2, it's of x. This is j of 3 by 2. So 2 alpha is 1. So 1 upon x, j of half x. Or j of 3 by 2 x is equal to j half x. So this is 2 by root pi x. From this term we have sin x by x, and from this term we have cos x. As x tends to 0, the factor in the numerator, this is 1, this is 1 as x tends to 0, so this is 0 by 0. So this is 0 by 0 form, it is of the 0 by 0 form. So we can use L'Hopital rule to find out the value of j of 3 by 2 at the origin. Here we should adopt some other technique. we use it as 2 by pi square root x to the power half. Then for this I write 1 minus x square by factorial 3 plus x to the power 4 by factorial 5 minus, this is for sin x by x. Note that sin x is, as per Maclaurin expansion, sin x is x minus x cubed by factorial 3, and this has been divided by this, and this is minus 1 minus x square by factorial 2 plus x to the power 4 by factorial 4 x to the power half. This 1 cancels out, and this part. This is 1 upon factorial 2 minus 1 upon factorial 3 times x square. So, sorry, this is minus. Then x to the power 4 part. This is such terms. So when we adjust this, we get 2 upon pi to the power half. This is 1 upon 2 factorial minus 1 upon 3 factorial to the power x to the power 3 by 2 minus 1 upon 4 factorial minus 1 upon 5 factorial x to the power 7 by 2 plus higher order terms, and as x tends to 0, this goes to 0. So we see that Bessel function of order 3 by 2 at the origin is 0. Now we come to the Bessel function of order minus 3 by 2. If we put alpha is equal to minus half, so this will give you Bessel function of order 3 by 2. Again, so gives equation 3 alpha g of minus 3 by 2 of x plus j of alpha is minus half, so this is j of half this is alpha is minus half, so this is minus 1 by x, j of minus half of x. So j of minus 3 by 2 of x is equal to minus j of minus half of x by x plus j of half x. This is pi x taken common, so this is cos x by x minus sin x. As x tends to 0, this part has essential singularity because cos tends to 0 and the denominator goes to 0 as x to the power 3 by 2. Cos x goes to 1, so it is of the form 1 by x to the power 3 by 2, which has an essential divergence, and this goes to minus infinity. So j of minus 3 by 2 as x tends to 0 tends to minus infinity. So from this discussion we see that j of half and 0 is 0, j of 3 by 2 and 0 is 0, j of minus half as x tends to 0 tends to plus infinity, and j of minus 3 by 2 of tends to minus infinity. From this we can conclude that Bessel function of half integral order is g0 if the order is positive, and it diverges to plus minus infinity if the order is negative. The higher order Bessel function of half integral order can be generated in this way. We can also use alpha is equal to half to this relation and we can get a relation involving j of plus minus half with j of 3 by 2, sorry, j of 3 by 2. Now with this discussion we switch over to the orthogonality relation of Bessel function that will be taken up in the next class.